to the debate. Today, we're focusing on, well, on a fascinating topic, neuromorphic computing, or NC. It's an architectural philosophy that's explicitly designed to mirror the structure and the function of the human brain. We're talking artificial neurons, synapses, even electrical spikes.
And our source material makes a really striking claim about it. It frames this not just as, a better way to do AI, but as a genuine rethinking of the whole concept of computing.
Exactly. And that framing, that huge claim, is really where the disagreement for today lies. Core question is this. Do the profound sort of theoretical architectural advantages of neuromorphic computing fundamentally redefine the field today? Or are the current practical limitations, the real-world problems with implementation and programming, keeping it stuck in a highly specialized and frankly unproven niche? My position's pretty firm. I think this architectural shift, especially its solution to the von Neumann bottleneck, makes NAC the inevitable foundation for future intelligence.
And I come at it from a very different angle. I'd argue that despite the conceptual elegance of the design, the technological and software hurdles we're facing right now, the instability of the components, the sheer difficulty of programming these things, it all means that NC's promise is still largely theoretical. It is simply premature to call it a fundamental paradigm shift when the gap between the blueprint and a scalable, reliable reality is just so vast.
Well, let's start with the necessity then, because I think it's the fundamental power constraint that makes this whole thing inevitable. Traditional computing architectures, they struggle profoundly with two things when you try to scale them to complexity. One is massive power consumption, and the other is slow processing because of that constant data transfer, the memory processor divide. The human brain, on the other hand, handles massively parallel processing using a mere 20 watts. NC is designed from the ground up to capture that efficiency. The solution, architecturally, is to adopt local memory. Computation and memory are they're unified in the same component, which is effectively the artificial synapse.
Right. And I will grant you that the concept of the spiking neural network, the SNN, and that event-driven processing, it's incredibly powerful. The idea that you only process data when a spike actually occurs, rather than on some global clock cycle, that's how you get that spectacular energy efficiency. I absolutely acknowledge that advantage. But an elegant theory doesn't automatically create a practical revolution. We have to focus on the implementation. For me, the primary constraint isn't just that it's hard to program, it's the profound structural difference. We completely lack a universal neuromorphic software stack. The real difficulty is in how we're supposed to train these networks.
But training is a solvable problem of methodology. The architecture itself is the permanent solution to that inefficiency. When we talk about local memory, what we're really talking about is using crossbar arrays of memristors. Now, the memristor holds its state, its weight, as an analog resistance value. When a current, a spike, passes through, the computation happens right there, in the memory element itself. This isn't just memory near the processor. The memory is the processor. This unified system is what allows for continuous adaptation, for online learning, the ability to learn on the fly, which is absolutely essential for real-time edge applications like robotics.
Okay, I'm sorry, but I just don't buy that. I don't buy that the architecture is sound if its foundational physical components are fundamentally unreliable. And let me tell you why. The source material explicitly calls memristors not yet perfect or mass manufactured. You're building your entire revolution on a metastable component. We're talking about known issues like resistance drift, where the weight of that synapse just changes over time because of temperature or electrical stress, even when it's not being updated. You see huge cell-to-cell variability. You see challenges with reliable read-write cycling. A modern data center is built on billions of robust, predictable transistors. A paradigm can't shift if its core component, the memory that is the computation, is inherently volatile and struggles with long-term reliability.
Right, that's an interesting point, though I guess I would frame it a bit differently. Every foundational technological leap starts with imperfect components. We faced very similar manufacturing hurdles with early solid-state transistors, didn't we? The elimination of the von Neumann bottleneck is a total re-architecture.
It fundamentally changes the physics and the economics of computation. You mentioned the 20-watt brain. That spectacular efficiency is the reward for accepting the initial instability of analog processing. We are trading the robust, predictable digital world of CMOS for the massive parallelism and low power that's inherent in analog resistive memory. And that trade-off is absolutely necessary for any truly intelligent system that has to operate at the milliwatt level.
But that reliability issue isn't just about maturity. It creates entirely new systemic bottlenecks. By combining memory and computation so tightly in that crossbar array, you introduce massive complexity in, say, thermal management and I/O integration. The heat you generate during computation is literally right next to the memory structure, which makes that resistance drift you're trying to minimize even worse. So you solve the memory bottleneck only to create a thermal bottleneck or a reliability bottleneck. And on top of all that, the fact that it is, and I quote, hard to benchmark these systems, that's a really deep-seated problem that prevents the kind of validation you need for mass adoption. And this all leads directly to the scope of NC. You're arguing for a general paradigm shift, but its current proven advantages are all highly specialized. The source material emphasizes that NC is perfect for edge AI. It specifically cites low-power, real-time sensory tasks. Drones, hearing aids, smart sensors. It's creating a new class of intelligent machines for very specific low-power applications. If it's a true general paradigm shift, why should we expect it to ever supplant generalized CPUs and GPUs that are used for high-throughput, non-event-driven calculation in big data centers?
I see why you think that, but let me give you a different perspective. Specialization is the critical first step toward any paradigm shift, especially when that specialization addresses the most profound failure point of the existing technology. NC is targeting exactly the areas where traditional computation fails entirely, that need for low power, real-time interaction, and continuous adaptation. Future computing isn't going to be defined by static data centers running massive pre-trained models. It will be defined by millions, billions of devices interacting with the physical world, needing immediate sensory input processing, needing a kind of robot nervous system capacity. The ability to run continuously on 20 watts, that's what makes NC not just a niche, but the only viable foundation for that next generation of tasks.
But that ignores the vast majority of computational work that's done today, which is high throughput, structured data processing, database queries, scientific simulations, training these massive deep neural networks. For those tasks, the density and speed of traditional accelerators like TPUs and high-end GPUs, which are optimized for dense matrix multiplication, they are just superior. NC, because it relies on sparsity and temporal encoding, inherently sacrifices that raw numerical throughput for power efficiency. It's a fundamental trade-off of adaptation versus speed at scale. To call a technology that excels at sparse sensory tasks a rethinking of the whole concept of computing is, well, it's a radical overstatement when it has zero presence in high-throughput numerical processing.
That assumes the demands of the future are going to look exactly like the demands of the present. As AI applications get integrated into complex, unstructured environments, I'm thinking robotics navigating dangerous terrain or autonomous vehicles reacting to novel traffic scenarios, the need for online learning, that ability to continuously adapt without connecting to the cloud, becomes paramount. NC's architecture, with synaptic plasticity built right into the hardware, is uniquely positioned to handle that real-world ambiguity that a massive static data center model just cannot. The shift is from centralized batch computation to distributed adaptive intelligence. That is the paradigm shift.
But the barrier to any kind of generalized adoption is still the software. Even if the hardware were perfectly mature today, we face a massive logistical and intellectual hurdle. You've argued that the programming difficulty is just a temporary barrier, like the early days of parallel programming. I would argue it's a structural barrier because the mathematical foundation itself is different. We can't just port established machine learning techniques like backpropagation effectively to SNNs.
I acknowledge the difficulty in programming them, I do. But this is typical of any architectural leap that provides an exponential gain. Engineers had to learn entirely new methodologies for parallel computing because the payoff was worth the pain. We're just seeing the same process here.
I don't think you're grasping the depths of the difference, though. Training SSNs often requires entirely new algorithmic approaches, like spike timing-dependent plasticity, STDP, or other localized learning rules. They're biologically inspired, yes, but they're mathematically far more complex than standard backpropagation. We don't have unified, robust libraries. You can point to Intel's Loihi or BrainChip's Akita, but those are specific corporate implementations, not open, standardized platforms.
And yet, their very existence proves that the solution is commercially driven and, ultimately, achievable. The capital is flowing there because the energy savings are simply too profound to ignore. We are moving from watts to milliwatts. That is a scale of efficiency that justifies the immense capital investment required to retrain engineers.
That's a compelling argument, sure. The energy necessity is real, but have you considered the economic inertia here? The current software ecosystem, Python, TensorFlow, PyTorch, is supported by millions of engineers and billions of dollars of investment globally. To transition engineers from established software models that rely on simple, dense matrix math to architectures that are inherently hard to program because they require temporal data encoding, that is a monumental undertaking. The economic friction alone prevents a mass revolution. Until programming SNNs becomes democratized and scalable, accessible to researchers outside of these hyper-specialized labs, the potential just remains locked away.
But the fact that SNNs allow for on-chip learning is the democratizing factor. They allow complex AI to run entirely locally without connectivity, which eliminates the latency and power cost of constantly talking to a data center. This opens up entirely new applications that were simply impossible before because of energy limits. This is a foundational redefinition of where intelligence resides and how it operates, on the edge, in real time, adapting continuously.
If that adaptation relies on unreliable memristors and highly specialized fractured software platforms, then it's merely a high-potential research direction. It is not a paradigm shift for generalized computing. Reliability and standardization, that's what defines a paradigm shift. High-risk innovation defines a niche.
The debate, then, really lies in where you place the fulcrum. Is it on the necessity of the architectural solution, the biological inspiration, the removal of the von Neumann bottleneck? Or is it on the current,